Thank you, Stephen. It's good to be back at a BSD conference after about 10 years. So glad to be here and meet familiar faces and new faces in person. This talk is more or less identical to the talk that my co-programmer Santosh Raju presented at EuroBSDcon earlier this year. And we've done a little bit more work on it, but nothing to show for it that we've published. So I'll just stick to the baseline of the talk. And essentially, what I'm hoping to do with this talk is not really to present the guts of the development cycle or the experience, but rather to kind of share the opportunity that I realized after 10 years of kernel programming that a certain methodology or approach to coding can actually bring to kernel programming. And I feel like because this code was quite intrusive and at the deepest part of the VM subsystem, typically you'd expect a lot of chaos because NetBSD's VM powers about, I think it's about 11 CPU architectures and about 70 platforms. So it's really like a huge amount of dependencies, and a lot of things can go wrong. So really, most of the technical details are in the man pages. We won't cover that. But I just wanted to kind of go over the broad sort of storyline with the hope that that I'm not preaching to the choir, and actually there are people from other BSDs and also diversity of port maintainers in here. So it's a little bit of evangelism as well, if you bear with me. All right. So this is the background. The background is that all the current BSDs have a very simple implementation for keeping track of RAM on the machine. Essentially, it maps to a very simple static array. And this is the famous VM fisseg max hash define that has come up for discussion when large amounts of RAM show up, or the in the x86 world, the EA20 map is very fragmented, and then things happen. And this is obviously from a really long time ago, when RAM was not so much, and the layouts were not as complicated as they are on modern machines. And so the discussion about this, or the idea for this project came up from the need for virtual machines to have memory added and removed dynamically at runtime. And right now we have a balloon driver, which is a hack to kind of remove allocated memory from a virtual machine. But there's no way to put more in for NetBSD at least, and for the other BSDs, I believe. So we said, okay, how do we take on this problem? This is really, the tentacles go really all over the place. It's really hard to, pull things out and separate them. Where do we start? I mean, there's VM-fysmem is a global variable, and it's strewn all over the place, and it's used, by every bit of the VM code everywhere. So the first job, obviously, was not to try and do any hot plugging, but to clean up. And so we said, okay, we want to use something more dynamic than an array, but we want to clean up so that we have a hold on sort of, the complexity. Otherwise, it just explodes. So we said, okay, we'll clean it up. And so that's when, the idealist, shows up. And, okay, so now we've got a chance for a brand new API. So I went away and designed this massive API with, like, tags and cache attributes and everything. And then I had it all spec'd out, and we wrote ATF tests for it. And then we ran it by people who actually had a lot of experience designing and building these things, and they basically came back and said, "Sorry, this looks interesting," but and we hadn't, it hadn't got in the kernel, so Chuck Silver was really helpful with a lot of feedback. He helped with the initial integration of UVM, the virtual memory management manager for NetBSD, into the kernel. And so, idealism gave way to sort of pragmatism, and we decided to kind of work the other way. So we thought, okay, we'll try and put what exists and what we've cleaned up to kind of interface with the rest of the kernel through a simpler API. And so that would mean that we'd separate out the existing API and expose it via header files and hide everything else in file scope. And then most importantly, have a way to unit test all these functions. This is the first time in, I think, maybe 30 years since the BSD projects have begun that actually these functions were tested, actually, using unit tests. So, so it was, it was kind of interesting. And so a lot of the detail was basically trying to get this situation going. So like clean up the code, sort them into separate files, and then try and organize getting the specific functions unit tested in a disciplined manner. And we made the choice to kind of do this first. So like this was in the live current tree. So, because you can go away on a limb and try and kind of, create APIs, and then everything breaks when you try and integrate. So we use the approach that before we try and unit test everything, we'll try and do the reorganization in the live source in a way that doesn't change functionality, but then we can also sort of put the tests on top of them. And so we initially got UVM-FISSEG and .c and .h, the code reorg, into current before the tests were in place. And now it was in a position where we could start looking at the unit tests. And Santosh actually did this entire project on a Windows laptop with Cygwin. So that's testament to NetBSD's code cleanliness. So the reorganization didn't really affect the ability for NetBSD to boot, and life went on as usual in current. We didn't mess with that. But then this is where sort of the modifications now started getting interesting. So we essentially figured out how to now everything to do with the array management, the segment array management went into that file, uvm-fisseg.c. And so now you've got like a little module that you can actually test. And so we literally did a hash include uvm-fisseg.c inside of a userland test rig. And so now we had enough to compile a separate userland binary, which then we could run unit tests on. And the uvm-fisseg.c that we were using was not a copy, it was a live copy that was in the kernel. So, everything that we were testing was already in the kernel, but we were testing it completely in userland, which was pretty neat. In that process, obviously, you have to export a subset of the kernel API to userland. Rump does this by namespace rehashing and so on and so forth, if people are familiar with rump on NetBSD. But this is much simpler. This code doesn't really use, a lot of API infrastructure. So, essentially it was kmem malloc being stubbed by malloc, things like that. So it's fairly straightforward. So now we could focus on the guts of the move from static array to R-Bree. And so we said, okay, well, what are the other options? And we went through the iterations of that, and essentially it boiled down, the decision about R-Brees boiled down to what was available that was easiest to use and gave us the best promised performance. And literally, NetBSD's R-Bree implementation was just right there waiting for us to use it. It made technical sense because the previous code had, an array, if you want to insert, things into an array, you have to copy over, bits of data and then insert And so there's a lot of overhead, and so there were a couple of algorithms using hash define. So you could, there was hash define for binary searching for specific items in the array, or for random search, and so on and so on. So there were 3 options, and we said, well, all of that goes away, and the R-Bree tree takes care of that. And so we just have one. There's no compile time option now for searching in this array of segments, of memory segments. So there are no multiple strategies for maintaining segments, and obviously less code clutter. And yeah, there were a couple of other options. Q was anyway not an option because it was the worst of both worlds. But yeah, R-Bree tree was there, and we thought we'd go with it. And we also thought we'll do some performance analysis from Userspace because, hey, that's cool. So we'll come to that at the end. Some of the details. So essentially, the thing that's interesting for the rest of the VM system is, what does this bit of, what does this page offset in RAM point to? What the VM page structure, basically. So I want to look, given a physical address, I want to have the pointer to the data structure that represents that page of memory. That's essentially what this array gives you. And so we essentially abstracted the idea of the index into the segment with a sort of abstract data structure called uvmphysec_t. But initially, before we did that, we ensured that this abstraction was sitting on top of the array itself. And so yeah, I mean, I went over this again. It was quite interesting. It was a huge number of architectures to port to. So yeah, so some of the challenges here. And then obviously the performance implications. So we'll look at that later. So we introduced, certain sets of abstraction. So as you can see, previously you had global variables being, used outside of the module, and then you would have sort of iteration through a macro, and then we kind of hid everything behind explicit function calls. And it can be argued that, this is less performant, but then the setup, and many of these loops are actually run only at boot time or during Hotplug itself. But when it comes to actually searching for things when the system is running, so there's not really so much of a hot path. So we thought we'll run with it, and then we'll see how it goes in terms of performance. This function came up because it was interesting to understand what a valid segment was. A lot of systems code sort of ad hoc puts in a placeholder value like -1 or null or something to signify that an entry is invalid. And it got interesting because we had to make this explicit and say, okay, what does this index point to? Is this, is this a valid address, or is it a valid index? And why is it a valid index or not? So we wanted to pull out that assumption in terms of tests. So literally the approach was, if there's anything that we had in doubt in terms of semantics or state, we'd write a test for it and make it explicit. And this was really useful because I think this kind of took care of the idea of the hero that we got introduced to this morning, because the hero can be reduced to ATF tests. I think this is my discovery. So a lot of the heroism is holding the state in your head and being able to process that data and make a call on design. But I feel like if you can make it explicit in these tests, and you can automate the open source hero into tests, by and large. I'm not making this claim, but at least from my own ego, it was interesting to, I became less relevant, basically. So we it goes to, it doesn't need to be mentioned that we did quite a bit of test coverage, and all the tests, they're live tested using Anita in the NetBSD build system. So these are part of the formal test rig for NetBSD. Essentially what we did was we got the tests running so that the objective was for the semantics and the state information to be exported explicitly in these tests. And we made sure that the current implementation could be tested rigorously first, before we touched it with R-Bree tree. We said we want the current implementation to be, running under these tests. And so, yeah, and so, where are we? Sorry. Yeah, we had some interesting situations. So the original idea for vmfseg, the array, was explicitly meant for boot time. So you boot up, you populate your array after machine-dependent code passes through your memory, hardware-dependent memory tables, and then you populate the array, and then that's it. You don't touch it afterwards. But we were interested, obviously, in being able to plug in new memory and pull out bits of existing memory. And so immediately, that brings a lot of interesting issues, especially fragmentation and how to manage stuff. In the process of this integration, there were certain assumptions, like, for example, page first load was just expected to succeed, because if you couldn't, if you couldn't register a physical page during boot time, then that's like something serious is wrong, so you panic, basically. And so that was the assumption in the boot code. It was avoid UVM page first load. Well, that's not great for testing, because we need to know if this function actually, did the right thing or not. And the function should have some way to return that information. So we essentially edited the function, to return what happened to that load. And so there were similar kinds of things that were, modifications that we did. So, yeah. So sorry, I'm going ahead of myself here. But essentially, again, just to reiterate that point, it was to make the test framework pull out all these assumptions that were inside of programmers' heads, and just put it down in writing and make it as explicit as possible. So here's a slightly subtle one. We kept getting this failure for get previous segment. So given an array offset in that physeg array, can you give the function is asked, can you give me the previous entry? And obviously, it would be, in an array, it would be just, index minus 1. But this was failing for us. And this was kind of the situation in which that was happening. And for a minute, it had me wondering what the heck is going on. And at this point, we had the R-Bree implementation as well. So we were testing both together, side by side. We had the test running on the static array implementation and the R-Bree implementation. And what we discovered was that the reason that getPrev was failing was because the assumption of what of the property of the handle that we were passing through to that function. So for the array, it would be the index value, but for the R-Bree, it would be a pointer. And there were certain implications for that, which I'll talk about in a second. So this is the static array implementation. So B is a loaded segment. The system knows about it. It's already been UVM-physeg loaded. And therefore, the index, if you were inserting segments, would be in increasing, monotonically increasing order. So 0. And then if a new one were A was inserted, what would happen would be that would get copied over, and then A would go in and 0. So you can see here that to refer to B initially, you would want to refer to the index value as 0, but then once the insert has been done, 0 refers to A. So this means that the handle was not immutable. We were making the implicit assumption that the handle was immutable, but in this case, the handle was not immutable in this implementation. And so, this brought it out. Whereas for the R-Bree, there's no problem because the pointer remains the same. So the handle is immutable. And so essentially, again, we exported that assumption into a test and said, okay, well, we'll slap a test onto that so that we know exactly what's going on. Yeah, so now the property, the behavior of both implementations is explicit and is explicitly tested for. Right. At that point in time, we were also supporting conditional compiles of the static. In fact, we still do have conditional compiles of the static. So you can use both in NetBSD right now. So you don't need to actually use R-Bree, you can also use the old static implementation. Right, so guess what happened? Yeah. So, so at this point, I was on my own. Santosh wasn't very familiar with the NetBSD system itself, and it was. I was pretty pleased that I was able to break down the problem in a language and in a context that he could understand as a Userspace programmer, and he was happy that he could actually get some work done on kernel code. But at this point, I was on my own basically, and I must give him a lot of credit. He's an amazing programmer, one of the best I've met actually. Well, that happened. And normally, at this point, I'd be panicking. Because, like, if I didn't have all the state information out there, it's the VM system. There's, like, a whole load of things that could be going wrong. But that wasn't the case. I mean, we had the tests, and we knew exactly what was going on. So we could actually flip assumptions inside the tests to figure out what was going on. And we quickly realized that the tests themselves assumed that malloc would always be available, obviously, because the tests run in Userspace. But obviously, the kernel doesn't have malloc running when it starts off. You have to figure out how to present malloc to the kernel that's booting. So that's a bootstrap problem that's very peculiar to a boot up situation. I think FreeBSD has a VM API, kind of, which does it in a very kludgy way. I forget the name of the API now. But anyway, but that's in a different context. Anyway, so essentially what we did was to kind of provide, so we tweaked the code a little bit so that we could have backend functions to do the allocation, a little bit like the pool allocator. I don't know if people have used the pool allocator, but pool cache allocator. But basically, your slab allocators, I think, have this backing function thing where you can, allocate either device addressable memory or actual, system RAM memory. But anyway, we used the same kind of approach. So we had like a callback function that would get initialized at boot time, which did the static allocation for boot time RAM. And then once we figured out that page init done was, done and KMM alloc could work, then we'd switch the allocators to the regular kernel memory allocator. So that was a little bit of a twist in the story, but yeah, I mean, again, we got that. So again, that assumption, we put it out in tests. So we explicitly put the assumption of boot time allocation versus runtime allocation inside of tests. At this point, more or less, x86 was working. We hadn't integrated code yet, mind, because you can't do that. I mean, there's 70 architectures going to get breaking if you start pushing code. So we started looking at, okay, so we're trying to, fragment memory and, hotplug and replug memory. And we started looking at the fragmentation problem. So you have a segment, and then so how NetBSD does this is that there is an array that essentially holds the physical data structures of all the system pages in memory. Now, segments are not at page resolution. Segments can be like a 1 gig segment followed by 1 megabyte segment followed by so on and so forth. But pages are 4K pages on NetBSD, I think, on most architectures. So PGS is an array of VM page structures, and not pointers. These are actual structures. That's where the actual data about the pages are stored. So PGS is really important because, again, we go back to the array problem where, as we saw in VM segment, that was an array, and then PGS is an array as well. So now we've got the same problem coming back at us. And we were like, oh my gosh, now are we going to have to use the R-Bree again, have to go over the whole thing again? But extent to the rescue. So extent is a really cool extent manager. So any namespace you give it, it'll manage the fragmentation, insert, remove operations on any namespace. It doesn't have to be memory. So it doesn't make any assumptions about backing, or you can tell it not to make assumptions about backing memory. And so that was it. We'd just plug that into the PGS array management. So instead of manually going and trying to mess with the PGS array, we just said, okay, well, we'll use extent. We'll register the entire PGS array namespace into the extent, and then just tell the extent manager to do it for us. And it was brilliant. It just worked. It was plug and play, literally. And so at this point, we were ready. So yeah, at this point, things were going well, and Nick Hudson mostly and Maya helped me integrate most of the code. And again, like what could have been a real mess, it was like 2 weeks, and most ports were like done. I mean, 70 architectures. I was pretty impressed. It could have been a nightmare, but you know, the methodology really. So the hero didn't do it. The tests did it, I think. Performance is really interesting. I mean, it's really simple performance testing on for this code base, because all we're interested in is how fast can you find you know, a segment given a physical offset. That is literally the fast path operation in this whole API. And so it was really, and there's essentially a macro that wraps over this function call. So literally, we just had to performance test one function, and that was pretty straightforward. So what did we do? Well, we had, you know, these tests had to factor in the fact that there were fragmented memory segments, because this was not the case previously. Before Unplug was available, you know, all the segments would be contiguous. There's no big deal. You know, finding out, the same algorithm could find them out. But here, if your segments were fragmented, then your R-Bree tree starts getting, you know, filled up in not necessarily symmetric ways, right? So, so we wanted to see what impact that had on performance. And so what we did was we kind of faked the, so we used random to essentially fake the effect of a running system. So we used the random system call to essentially sort of spread out the physical address offsets of what, so okay, so you could test it saying, okay, from 0 to the end of RAM, you know, run through a loop and see what physeg find gives you. But in this case, you know, you know, that's one way to do it. Or we could just sort of randomly look up offsets, and that's what we did. So so we did a you know, 100 calls to 10 million calls kind of breadth of calls, and again, you know, random. So on a real running system, physical addresses are not necessarily randomly looked up, right? I mean, there's a lot of caching, a lot of code that keeps running repetitively. So this is not really an indicator of the actual system performance. And this is sort of work to do, or maybe a comment about how this kind of testing can be done in a slightly different way. Load testing, I think, is not really mapping straight onto ATF testing. But essentially, yeah, we just, you know, we used what we had, and all this stuff was done in Userspace. And so, yeah, so we, you know, we applied different scenarios, so fixed size segment, fragmented segment, just to see what effects it had on the performance. And we'll get you some nice graphs in a minute. But yeah, so this is what it would look like. Numbers would be pulled out like this. And then, yeah, and then we got tables. And you're welcome to look at that later on. But you can, yeah, I mean, so you can see you know, you can make a quick scan through the tables, but the top one is R-Bree tree and the bottom one is static array, and you can immediately see that the R-Bree tree implementation is taking more time, you know, to find segments. So I wanted to see, you know, how bad it is. So yeah, this is just a sort of, you know, testing between 10 million segments and 100 million segments kind of thing. So yeah, so this was the statistical kind of methodology we used because we were using random. So we had to kind of compensate for that by using, making a statistical approximation about how, you know, how much confidence do we have in the actual number we're getting. And so we kind of, you know, we stuck to a margin of error of 95%. I didn't do this work, so if you have any questions, I'll redirect them to Santosh. But anyway, so that's the number, 5.59% degradation in performance, which, you know, depending on how important it is for you to plug or unplug your memory live, is a design choice that, you know, a manager can make. So there we are. And right. Yeah, so that's the details of fragmentation and how we did the tests and colorful graphs. But you can kind of get an idea of, yeah, so those are graphs of the average, maximum, and minimum times for different, you know, numbers of segments that were being tested. And yeah, just to go over some of the things that we were probably missing. Originally, when I designed the API, the ideal API that had all the you know, cache attributes and this and that, we actually looked at rump testing, testing on rump. But the problem with rump was that there was a whole load of assumptions inside of rump and a whole load of dependencies that we'd have to bring in. And so we abandoned that. But I think for load testing, rump is pretty good because it can interface with actual user space workloads and exercise your code paths. So I think rump is interesting for load testing of this kind of behavior. Yeah, code. Well, we could have a bit more code coverage. I mean, that's the question of how much time you have to address. But more importantly, I think maybe if we could get some live numbers as well to make a comparison to the numbers we got with user space testing. With dtrace. I'm not sure dtrace, I haven't used dtrace on NetBSD, but I don't know what the state of it is. Anyway, maybe we'll get some feedback on that later. So yeah, this was the big, you know, moment of enlightenment. You know, existing techniques, nothing fancy, no heroism required. Just, you know, apply standard techniques and you can do cool stuff. I definitely had a much less stressful experience than debugging Zen interrupt handlers. So, so this is pretty cool. And obviously, you know, it did help that there were APIs inside of NetBSD that made the least amount of assumptions about what those APIs, the context in which those APIs could be used. For example, you know, R-Bree could be, it's a user space library, but it can be used in the kernel, or the extent, you know, API does not assume anything about the nature of the backing RAM, for example. So really cool to have that kind of tooling available inside of the kernel. So, I mean, literally this sort of pitch is for people who have access to or know about hardware that can do hotplug outside of virtualized environment, or even inside virtualized environment. I think VirtualBox, QEMU has an ACPI interface for hotplugging that I had a look at, but it was way, you know, our ACPI stuff is a bit shaky at the moment, so a little bit more work required for that. Zen is the easiest to do, and I've done like a really simple stub plug implementation. What's missing is that if you want to unplug code, your driver needs to kind of, so there's a little bit more work required for unplug, because obviously you can't just unplug memory that's being DMA'd to, or like, you know, memory that, you know, is being used for something. So there needs to be a way to figure out, you know, if a page that you want to unplug is in use or not. And that, you know, this can be, I mean, this enables that, but it doesn't do it for you. So if you're writing a driver, obviously you have to, you know, there's a little bit more work for that, and also exporting this functionality to Userspace. You know, if you have a RAM control kind of utility that talks to the kernel and says, pull out this offset of RAM or whatever. So that API needs to be designed and so on. But the basic interface with the virtual memory manager is in place, and it's reasonably robust, I think. I haven't seen any complaints of weird page faults or panics on various architectures, so far at least. So I'm keeping an eye on it. But so yeah, and the cool thing is that the VM system is probably the, you know, the most, one of the oldest in pedigree, because obviously all the BSDs started off from a similar VM system. So I feel like other BSDs could actually benefit from this work. So FreeBSD especially, I've had a look at their VM code, and but you know, they could benefit from this stuff. OpenBSD, I think, uses UVM, so I think it should be fairly straightforward for them, but FreeBSD might need to put a little bit more work into it. Thank you, all these people. Philip's here. And yeah, NetBSD Foundation. We coded this by the beach. We spent 4 months. It was brilliant. I highly recommend it. Philip knows about it. He's been to the venue. Yeah, and yeah, that's the credits. And yeah, thank you, everyone. And yeah, 5 minutes. Yeah, we got 5 minutes for questions.
Can we kill the balloon driver now?
Well, the balloon driver could use Hotplug. Yeah, right now the balloon driver uses the hack that it uses kmem alloc to reserve memory and then keep it away from the rest of UVM from reusing it. But it also interfaces with the hypervisor. So there's an assumption there about how that API works. So we could reduce it to an API that's kind of named balloon, but does something else. Should probably be called Hotplug now. But yeah. But yeah, the kmem alloc stuff would change.
For the benefit of the video, can you explain what Anita is and how it worked in your workflow?
Yeah, so Anita is a continuous integration setup that NetBSD has where all the ATF tests inside of the NetBSD source tree, correct me if I'm wrong, are kind of, so your source is built and then all the tests are run. I'm not sure what the frequency is. Go on, sorry.
Anita is a Python, wrapper that actually takes a build, and after that it spawns up either a UVM or another emulator, runs a NetBSD install, from scratch, and then starts running the tests. So it builds a new environment, a new system, make sure that everything works from the installer to actually running the full test suite, and it completes. And runs, there is in redlang.netbsd.org, you can go and follow the link, and it has several architectures that run daily and others that run on emulations daily and others that run on real hardware, weekly or whenever people get to run them.
The E386 runs 8 times a day. Spark we aim to run twice a day, and others about at the same frequency.
All right, I hope that answers your question.
Now the real question is, so first of all, I think that we don't really unplug and plug memory all the time. This is kind of an event that doesn't happen too often. So optimizing the whole thing to an arbitrary seems to me like kind of an overkill, right? Because you could just say stop the world and rebuild your array. Isn't that a feasible thing? Or what other thing does arbitrary buy you? That's the first part of the question. And the second part is that the unplug is the most interesting part of it. And the reverse lookup is what you want to have, really, is to basically have the subsystem ask, okay, who's using those segments that I'm trying to unplug right now? And if it's a device driver, the device driver needs to relinquish them. And if it's a process, we have to wait for the process to finish, or we decide to kill it or something, right? Yeah. And that's, have you given any thought on that?
Yeah, this is a trick question. Okay, so I have fleetingly thought about it, and we when we did the work, where we really had to have deliverables. We wanted to put it at a point where we actually had some functionality. And so initially, I did actually go around and write a very rudimentary RAM control tool just to think about how a user would interface with the kernel. But it turned out that that is a house of cards that's going to fall very hard. My thought about this is that if we can incrementally start, so the arbitrary question I'll come back to in a minute, but my thought is that if we could have, if we could have users, so for example, Zen or any virtualized environment, is the immediate one that I can think of. And then, there's heavy metal architectures out there that have ACPI-based hotplug, and I'm not sure if the other architectures, Spark and so on, but I'm sure that the server industry has these hardware-mediated RAM plug-unplug things. So if we could have just the basic sort of plug-unplug operation for specific cases that are maybe that's memory that is not DMA'd or memory that is only allocated for a restricted set of things that can be tracked. So, for example, things like maybe some kind of cache, maybe. I'm not sure which ones, but we'll have to do the analysis. But a restricted set of these pages could then be looked at, because the state tracking, again, that's a huge effort to figure out the reverse lookup of what page is used by what subsystem, and then to keep track of all of that, and then to make sure that this particular page is not being accessed by anybody. That is a significant search problem in terms of search space. So yeah, Taylor. Yeah, I'll come back to that.
Is it often the case that you will want to use memory that you have hot plugged for, say, DMA or kind of driver-specific specialized purposes like that? Or could you prefer to allocate DMA memory from what is provided initially at boot, and prefer to provide hot plugged memory to, say, user processes where you could just you could unmap them and move the page data to another page, and then remap them and let the user space continue?
Yeah, that's a pretty that's a leading question, actually. So I think bus DMA already has, and this is a machine-dependent question, because one can imagine that there are architectures where hot plug memory can be used equivalent to boot time memory, and then there are other architectures like x86 where the first 16 megs is only accessible to certain types of DMA controllers and so on. So I think that is a machine-dependent question. Sorry, I missed the main part of your question.
So my question is, could you use this as a way to avoid having to do the search, the reverse lookup problem, and just
yes.
make the problem simpler by pretending harder cases don't exist?
Yeah, so that's kind of what I was leading to with when I was saying that we should probably try and restrict where unplug is done inside of certain categories of memory, or certain memory management APIs like bus DMA, or I can't think of something else at the top, off the top of my head. But yeah, so restricted categories of RAM could be, that's a start, I feel like. And then, different subsystems can then decide whether they want to use this or not. And then eventually, we could kind of have a sort of global. It's a complex problem. I don't have all the answers right now, but it definitely needs analysis. But I would say I would like to actually, when I get spare time, this was a funded project thanks to the foundation, but I would actually like to look at various use cases and start doing this, bits of categories of RAM, and then see if this API can be exercised. Got 2 minutes to answer Christos' original question, which was why R-Bree treat? I think the simple answer to that was it was available and it was easy to use. Yes, we could use something that was already available. So in theory, we could go back to the array implementation and make it do what the R-Bree tree does now, because we have the testing infrastructure in place to make sure that it doesn't fall apart. So actually, there's nothing stopping us from going back and reworking the array implementation to do exactly what the R-Bree tree stuff does. So yeah, so it's possible. It's just that was convenient, and we thought that it was not a very organized decision, but we kind of asked around about the performance implications, and we thought, well, we'll just find that number, 5.x%, and throw it out and see if people complain too much. And if they don't, then we're just gonna, push it in. But we're not forcing you to use it. You can optionally use the array implementation without hotplug, and then the R-Bree tree implementation with hotplug. And if someone's up for, doing a hotplug implementation of, using the array, you're more than welcome. I'm happy to, help with that. So. Thank you very much.